Okay, let's continue this morning session. It's my pleasure to introduce Professor Robert Friedman from Columbia University that is going to talk about deformations of singular Fano and Calabi-Yau varieties.
Thank you for the invitation. Yeah, I'd like to, this conference said in extension, I'd like to start with what does Kodaira-Spencer theory tell us? It tells us roughly that a deformation problem is governed by two finite dimensional vector spaces, P1, which is the space of first order deformations, and over think of these algebraically as over C at epsilon minus epsilon squared, and P2 is a space of obstructions. And although Dyer and Spencer didn't really think of it necessarily this way, the idea is you try to lift step by step. And if P2 is equal to 0, then there are no obstructions. And what that means is that every first order deformation can lift to an actual deformation. But most interesting problems, T2 is not 0, and then what Korenishi showed, under reasonable circumstances, there exists a holomorphic function phi from some neighborhood of the R's in T1, T2, and psi inverse of 0 is the sort of space of deformation. Some sort of vague sense. And of course, the best case is, well, you might not have T2 equal to 0, but if psi is identically 0, we say that the deformation problem is unobstructed. And that's, of course, the situation for it to have. So, as already known, Kodaira and Spencer, in some sense, you really, what you really want is you want, if you have the deformation over C of t mod t to the n plus 1, if you sort of lifted it to order n, you want to be able to, and so it lifts always to C of t mod t to the n plus 2, then it's unobstructed. So it's sort of, roughly speaking, enough to lift on one parameter arcs. And there's a general criterion for when you might be able to do this. This is the so-called P1 lifting. Which is due in sort of many different forms to Ron, Deline, Alamada, maybe self-mentioned Fontecchi, Bonetti, Gross, maybe others. But I won't really try to write it down, but I'll say what it means in certain examples that says that when this is satisfied, then the deformation problem is unobstructed. So what was the classic example of Kodaira-Spencer? You look at T1, which is, so here, let's say Y is a compact complex manifold. And you look at T1, which is H1 of Y with coefficient to the tangent bundle, and T2, which is H2. The usual deformation space and obstructed spaces. And for example, in the Fano case, where KY inverse is ample, then an easy application of the kind of vanishing implies that H2 of Ty is equal to 0. So this problem is unobstructed. And this can be generalized. So the generalized Fano case, which is due in various forms to Ron, maybe Atsarkov, Antevich, Pantev, Sano, and maybe others. It says if Kalo inverse is just nothing big, then you don't necessarily have H2 of Ty equals 0, but T1 lifting holds or some variant holds. So the deformations are unobstructed. So what about the singular case? What happens if Y is allowed to be singular? So let's assume Y is reduced, maybe with some sort of reasonable singularities. And we'll try to define. Then instead, there's the cotangent functors, or corresponding tangent functors. This is x1, maybe 1y, oy. This is a sheet of Taylor differentials. And T2, the obstruction space in this case is x2. And these are related by an exact sequence with geometric meaning. Which is essentially the local to global X spectral sequence. Of which the first few terms of this. So these are the global definitions of Y. These are ones which are locally trivial around the singularities. This measures how the singularities change or deform locally. So this is a sheet version of T2, and this is some sort of obstruction now. But the best case here is a good case, right, is if H2 of T naught Y is equal to 0. And what this means roughly is that the deformations of the global Y to the local deformations of singularities, this is a smooth. And you can think of that as saying that if you can locally deform the singularities, you can patch them into a global deformation of the compact space Y, and then there's some auxiliary free parameters floating around. Again, this is sort of rarely the case, but it's sort of a good model case to keep in mind.
Do you know if it's home?
Yeah, so here the T0Y are X sheet X, well, PI, XI of omega Y, OY. So T0 is POM, omega Y, OY, and that's the sheet of derivations. So, for example, a smooth case, then T0 just be the usual tangent. Okay, so in this context, let me just mention what does T1 lifting look like? This maybe this one is due to Kalamata. So suppose for all n, if I'm given a deformation, say yn of y over spec of an, and this is a sort of germ of partial smooth one parameter smoothings, and a lift of yn to a yn plus one over spec n plus one. So I've partially lifted it here. Then I can look at this group x1 So I have the global extensions of this sheaf by this sheaf, relative. And these are global x here. And this should be surjective. So if this is true for all n in all possible situations like this, then T1 lifting holds. And this is already interesting in the smooth case. And this is the theorem of Bogomolov, and Todorov, which says that if the Hodge spectral sequence P1 PQ equals HQ of Y omega PY degenerates at E1, and what the outer part of Y is Calabi-Yau in the sense that the canonical bundle of Y, so Y, so this is the Calabi-Yau condition. Then P1 lifting holds. And in particular, deformations are unobstructed. Okay, so the question is, what do we do in the singular case? And let me sort of give the prototype these results. So the prototype is construction due to Clemens. So here I start with a y prime, which is a Calabi-Yau threefold. And suppose that it has some smooth rational curves on it with normal bundle equals O of minus one plus O of minus one, and the disjoint. So, for example, by Hertzsprung, you can find lots of these inside of a quintic threefold. Then you can contract where the CIs get mapped to XI, which are ordinary Euler points. And Clemens noticed that you could get sort of very remarkable examples of non-Taylor Calabi-Yau threefolds if you could smooth them. So maybe I'm remembering this a little differently than her, but I think he essentially commissioned me to look at the deformation theory. And so you have the deformation theory.
I didn't know what to do with it.
I was in Utah at the right time. And so in this case, P1 of Y, H naught of P1 Y. This is just you can think of this as a direct sum indexed by the double points. There's one dimension for each, and then you go to H2 of P naught Y, and once you realize that this is H2 of omega 2 on the smooth one, then there's only one thing this can be, which is that the class of Xi goes to the fundamental class of the double curve sitting inside of you. And so what you see is, first of all, that a first order smoothing exists. In other words, I can lift these guys to here if and only if there exists a non-trivial relation in homology, summation AXI CI equals 0, where the AI are not equal to 0 for all I. And then secondly, you get an actual smoothing. So from this sort of naive point of view, what I'd like to do, I erase this. I'd like to kill, the sequence goes on further. And in this case, it's surjective because there's no local obstructions to deforming the singularities and they're isolated. So an actual smoothing, if the CIs generate the vector space H2 of omega 2. So that's that was a verb needed, but this is a long time before T1 lifting came along. So theorem due to, well, say Kalamata, Ron, and Tian, is that so condition 2 is not necessary. That was going to kill the obstruction space because T1 lifting. So I should say that of these three proofs, I think only the one by Kalamata is essentially correct. Okay, so let's not try to generalize that. So the goal will be to generalize this and see what we get. So I'm going to look at why compact analytic space and produce maybe there'll be stronger properties. It's natural to assume that it's Gornstein. That means it has a dualizing sheaf, which is locally free. And in the Fano case is that omega inverse is ample. The generalized Fano case is that this is nothing big. And the Calabi-Yau case would be where it's trivial. And I want to impose some kind of reasonable assumptions. So you might ask, what else can we impose? So, for example, reasonable assumptions for me. First of all, you might, I'll talk about non-isolated case as well. You might want to impose isolated singularities. And for example, that means that H naught of T1, this is generated, it's just a vector space. Otherwise, this is just some sort of sheaf on the singular locus and you don't really know much about it. Okay. And then another reasonable thing to impose, and this I'll do sort of consistently, is local complete intersections. Although, again, we see in dimension 2, we don't really need to do that. And that means that there's no local obstruction to deforming singularities. The only obstruction does not come from global issues. And then additionally, Well, there's a sort of maybe sort of a Taylor assumption, which let me phrase it, some kind of running rotation. I'm going to have I want to look at y hat to y. This will be a log resolution. In other words, the inverse image of the singular locus is simple normal crossings. E is the exceptional divisor, and so the log part means simple normal crossings. And I want to assume something else about it, which is that either that it's Taylor, or at least the DD bar lemma holds. So just some sort of thing that's going to guarantee E1 degeneration wherever I need it. And then the second thing is maybe a little more technical, but I'm just going to put it in now so I don't have to keep writing it, which is that I want to assume that H1 of OY is equal to 0. And that's automatic in the Fano case, and it's actually very typically satisfied in the automatic in the Fano case. In the generalized Fano case. And it's typically satisfied in the Calabi-Yau case. So usually if this is not true, you have an Albanese, and the thing's going to be a tall fiber bundle over the Albanese. So in particular, you won't have isolated singularities. But not. Okay, so let me just sort of briefly see what happens in dimension 2, and maybe just the Calabi-Yau case. Then Burns and Wall. Yeah, maybe I should say that the cases here are the Y. First of all, if it has rational double points, this is the case of canonical dimension 2, or famous rational Gorenstein. Then Burns and Wall prove that this is equal to 0. And because rational double points are hypersurface singularities, this implies that Y is smoothable and more. For example, if you want to look at the period map for K3s with rational double points, this is kind of an essential ingredient. And the other case is where if the singularities are, I'm just going to write down the names, simple elliptic or cusp singularities. This means that either there's a resolution, which is a smooth elliptic curve, or a cycle of rational curves. Then H2 of T naught of Y is equal to 0. So the deformations are smooth over the local deformations. So in particular, if local complete intersections, then they're smoothable. And then if they're in the general case, you can sort of play this game back and forth to try and understand when those kind of singularities admit a smoothing. And the point I want to make here is, so first of all, this case is the case of sort of genuine degenerations of K3 surfaces. Okay. The resolutions will be rational surfaces, typically, for example. So if you're interested in really degenerating the K3 surface to get something simple, you really want to look at this case. And in higher dimensions, okay, so I want to try to put this in perspective. in higher dimensions, what are the analogs of these conditions? And the first one is, so let me present definition why it has a rational singularity. At some point x, if and only if it's normal, and Ri pi lower star of what y hat is equal to 0. But there's a weaker property, right? I didn't know. There's a weaker property which is y is Dubois, I'm calling 0 Dubois of x. If then let's keep the normal condition, but then Ri pi lower star of y minus e is equal to 0. And it's a standard result that rational y is Dubois, isolated singularities to the Steenbrink and in general to Toba. The connection of dimension 2 is dimension 2, rational Gorenstein, rational level point, and Gorenstein and Dubois is rational level point for simple looping. So these are natural things to generalize higher dimensions, and then there's a fact about maybe that lower and Lloyd. If y is Gorenstein, then rational is equivalent to canonical. So in terms of the minimal model program, these are very natural singularities to look at. And Ishii, if y is Gorenstein plus isolated singularities, then Dubois is equivalent to log canonical. That's something that derives naturally the minimal model program. Okay, so to kind of go further, we have to sort of generalize to higher singularities. And the idea is that we want to look at sort of progressively milder conditions of singularities. These are sort of, to some extent, say the singularities are mild, but we want to impose further conditions. So again, I'm in a situation where I have a log resolution. And for simplicity, I'm just going to assume isolated singularities. Although you can do this in the non-isolated case, but it becomes considerably more complicated. And the motivation here is the following. Before I put a definition, if you think about this situation, there's sort of two natural complexes. Which are, in some sense, birationally invariant. So say that sort of loosely. The first one, I think, is the most familiar one, which is if you look at the log complex. And what this is, so its cohomology groups are birational invariants. They don't depend on the resolution. They just depend on the singularity. And what its topological significance is that if you look at the hypercohomology, the log complex, then this is equal to the cohomology of y hat minus e, but that's also the same as hi of y minus yc. So this complex computes the cohomology of the open variety, which you get by, well, you can throw away the exceptional divisor upstairs to the singular locus downstairs. Okay, and so this is introduced by Deline, who proved that if y is proper scheme with these additional assumptions, then we have E1 degeneration, the associated spectral sequence. Just like we have E1 degeneration for the usual Hodge spectral sequence. And the second complex is a variant of it, where you look at, instead of omega y hat log e, you put in a minus e here. And this looks more complicated, but, sorry, complex. This looks more complicated, but the hypercohomology of this complex is the relative cohomology of y hat with respect to e, and that's, of course, again, the same as the relative cohomology of y with respect to yc. So again, this is something you're interested in, only depends on the singular variety, not on the resolution. And again, there's so notice that if y is proper, then these groups are dual to each other, which realizes Poincare-Alexander duality. And in particular, the main thing that I care about is, again, this E1 degeneration of the spectral sequence. And kind of these are the standard ways that you can bring Hodge theory into the picture. So with these on the board, let me make definitions, so to speak, the higher singularities. And sort of for maybe historical reasons, it's the more complicated one that entered first. Definition due to get the names right. Yeah. I hope. Noon. Opa. Y has an M Dubois and Dubois singularity at X if, first of all, you have this there's a natural kind of a junction map here from Y to the first floor of this sheet. This is an isomorphism. And for all E less than or equal to M, and for all I bigger than 0, Dr. Different. All right, I will start. Maybe do I have lucky? Minus E at X is equal to 0. And there's a sort of companion definition, which is myself and Radu, which is that let me just look at the case of isolated local complete intersections. Y has an M rational singularity at X. If you have the same definition, but replacing this by the same, but replace the complex, we have the minus E here by the sort of more familiar complex And I should also add that in the case that we're going to be interested in, namely,
Or any just the vectors number.
so M,
Good. Oh,
this one holds for all P less nuclei. So it's set up so that M rational or M Dubois imply M minus one rational M Dubois. There's one extra condition at each stage.
Can you change the marker?
But to change the marker, am I fading? You know, I didn't expect a whiteboard. I brought the good chalk with me. So in the case that we're going to be interested in isolated and local complete intersection, and also dimensions y at least 3, then this condition, this is automatic. So the operative condition is the vanishing of the higher promote. And what you can show sort of easily is M rational implies M Dubois. But the really interesting thing is that, again, let me assume this case for simplicity, that M Dubois implies M minus one rational. And that's sort of peculiar to the local intersection case. And you should view these as sort of mild in the sense that if M Dubois, let's say, for M about half the dimension of y, and let me assume open intersection, that implies that y is smooth. So you get as M grows, you get sort of better and better singularities in some sense, and then about half the dimension, you get that this y is actually smooth at x. And maybe for a concrete example, in the case of dimension 3, here one rational. And let me assume local complete intersection. One rational already implies smooth. And one Dubois, but not smooth. And maybe I think you have to assume that not just local, at least in the literature, not just local complete intersection, but a hypersurface singularity implies ordinary double. But then in between one Dubois and rational is kind of a string of possibilities. Okay. All right. So that's kind of the setup that we'll use. And we're really actually, for our purposes, we're only going to care about n equals 1. Okay, so the unobstructedness results. The prototype was 1983. It says if the dimension of y is equal to 3, y is Calabi-Yau. Again, maybe some of the mild projectivity assumptions, and with rational local complete intersection singularities, then the deformations are unobstructed. And this is sort of partially generalized by myself and Laza a year or so ago to the case of dimension 3, and Dubois. But again, under the subject of isolated local computer sections there.
Do the first one, the example of Clemens?
Yeah, so for example, that includes the example of Clemens. And then and there are similar results for Fano, but take those. So so theorem, this is something Laza, so maybe a year or two ago. If Y is one Dubois local complete intersections, but not necessarily isolated. The definition of Y are unobstructed. But this is really kind of too strong an assumption. And there's sort of related results. Y is one Dubois and Fano. Then, and again, local complete intersections, but not necessarily isolated. Then, in fact, T2 of Y even better. So T2 of Y is equal, so again, it's unobstructed. And this is generalized by Tenie. If Y has Dubois singularities, so much weaker than one Dubois, but isolated local complete intersection. Again, you can show also in myself if Y has isolated rational local complete intersection singularities and it's generalized Fano, then the deformations are unobstructed. But you don't necessarily have this condition. Okay, so kind of, I think that's an upshot. It's the following here. Which again is heavily based on T1 lifting, says if Y is Calabi-Yau with the assumptions I had before, but in particular, what he sort of emphasized this one, some sort of Taylor condition with isolated, just Dubois, so much weaker than rational, local complete intersection singularities, then definition of Y. So that's sort of the limit of what I know about unobstructedness. Okay, so in the last 15 minutes or so, I was like, what can you use this for? And the general philosophy is that in some sense, having slightly complicated singularities actually makes your life easier. So you can get results when the singularities are more complicated because it gives you some traction for the deformation theory. And that sort of goes to local cohomology. So let me not really try to say that in detail, but let me try to write down what I think is the upshot of all of this. So this is a combination of myself and Laza, and plus the recent results of Tenie. So the idea is that you can sometimes smooth the singularities, but you can essentially always improve them. Okay, that's sort of the upshot. The theorem. So when you sort of sort out the contributions, so let Y be Fano with isolated. Remember, this is weaker than rational. And again, as always, everything should be a local complete intersection. Okay, so first of all, if all singularities are not one rational, which takes the definition of one irrational, then Y is smoothable. And I should note that in dimension 3, this is automatic because the one rational condition just is the thing that ever smooth to begin. Okay, and then sort of I thought the perhaps more significant thing is in general, Y can be deformed to a Fano variety with all singularities one rational. So you can always get a better model by deformation, meaning that the singularities become milder. And at that point, unfortunately, our techniques have nothing more to say. So the real interest, of course, is the Calabi-Yau case. Calabi-Yau isolated local computer section. And again, this is the weakest hypothesis to Bois singularities. And let me again emphasize that I want to assume this condition and a Kähler condition, but that this condition is probably inessential. So first of all, if all singularities are not one Dubois, then Y is smoothable. And secondly, if in general, Y can be deformed, so all singularities are one Dubois. Now, that's not really the end of the story because it doesn't really even cover the case that Clemens talked about. So to go further, we need another condition. So I want to consider the following condition. So here, X is going to be one Dubois, but not one rational singularity, which we called one liminal, meaning that it's sort of a boundary case. And the analog in dimension 3, for example, X is an ordinary double. Okay, so one has a topological invariant, the link of Y at X. Okay, which is just you take a small ball around X and you throw away the singular point. Okay, and that has a mixed type structure. And so you can look at these, right? You can look at this map, and there's just from essentially topology, there's a map to here. And of course, I can do this for all. B. And this is the analog in a sort of precise sense of the map in dimension 3 that I talked about earlier, where you take the generator and you send it to its fundamental class. And another analog is that, at least in the hypersurface case, and perhaps more generally, this is there as a result of Dimka and Saito, which says that if one liminal, so one Dubois but not one rational, and then Ger n minus 1f summation L sub x is one-dimensional. And let's just call this a generator. And that may or may not be true in the local intersection case, but certainly possible. So I want to introduce the following condition, which is the analog of the condition we had in dimension 3. So you look at let's call this map phi. So if there exists an alpha so there'll be a component in Hn of L sub x for each x. So there exists an alpha in the kernel phi such that for all x, alpha of x is not equal to 0. And in the hypersurface case, that just says there exists a linear relation summation over x and y sing of a sub x p by this generator, which is equal to 0 in H2 of n minus 1 y hat, such that a sub x is not equal to 0 for all x. So that's the analog of the condition I pitched. So now, now we get to put in the one liminal singularities as well. So the theorem is, so hypotheses before in the Calabi-Yau case. First of all, if condition star holds, and all singularities are one irrational, not one rational, then y can be smoothed. And perhaps more, again, more famous in general, if the condition holds, but I don't assume anything else about the singularities, then y can be deformed. To a Calabi-Yau with only one rational. In other words, you may not be able to smooth it, but you can deform the singularities to make them as good as possible with this theorem. Okay, so let's stop here.